So today I'll be talking about the detection of state-of-the-art censorship-resistant tools which actually embed covert data into multimedia streams. Unfortunately, as we know today, internet censorship is widespread around the globe, and usually it is sponsored by state-level adversaries, for instance, which try to control the information flow within these borders. Some examples are, for instance, the blocking of instant messaging applications, the blocking of certain internet websites for fighting so-called internet chaos, and we have some other examples such as blocking of websites due to offensive content, over offensive tweets, or also other political justifications, for instance, the Spanish internet censorship during the referendum in Catalonia. And all this blockage is usually allowed because adversaries are actually do have the technical capabilities to monitor and control the internet access within its borders. So in a typical setting, Alice, here is depicted on the left, tries to access some foreign service, for instance, the New York Times, but all her communications can be screened by the adversary. All this screening can be conducted by different techniques. So, for instance, if Alice is a journalist and tries to transmit some report to the New York Times, if her connection is unencrypted, so the adversary may, for instance, use deep packet inspection techniques to detect and prevent the transmission of such content to the website. Another way, if this connection is encrypted, the adversary can also perform other kinds of blocking, for instance, using DNS hijacking or IP blocking. However, not all communication channels within the country are blocked, and we can imagine, for instance, that Skype can be actually allowed to transit through the censored borders due to the economical advantages that this brings to the country's sustainability. And so, for instance, that these encrypted channels actually are important and for the development and deployment of covert channels. So how could Alice transmit her file to the New York Times using such technique? These techniques of embedding covert data into multimedia streams is often called multimedia protocol tunneling. So we can actually see that these text data will be transformed into a matrix of pixels, which can then be combined into the video stream that Alice will be transmitting through Skype. And thus, if the censor only actually tries to screen whether someone is talking through Skype or not, and if it allows Skype, so this connection is possible, the recipient of the call can then demodulate this data that Alice sent and then transmit it to the New York Times. However, multimedia protocol tunneling is not a silver bullet for fighting censorship. And this is because this technique, due to the changes in video compression, that a more difficult image to compress is sent towards the uncensored portion of the internet, the adversary can actually try to detect traffic patterns that deviate from the regular behavior of Skype calls. And usually this is performed by inspecting packet sizes or inter-arrival times, which are changed due to these compression capabilities. So it is very important for these systems to remain unobservable from sensors. And we call that property unobservability. And we'd say that the covert channel is unobservable if an adversary cannot distinguish a web stream that carry a covert channel from one that does not. And all previous works have actually tried to attempt to assess this property of unobservability using simple similarity-based classifiers, which just picked up the frequency distributions of packet sizes or interpacket times and try to see whether these match to a model of regular traffic. So it is very important to check whether these claims are sound, because if they are not, then this means that Alice can be subject to prosecution or even imprisonment. As a more deep down dive into the limitations of previous work, all of these different works have used different evaluation metrics. So authors would propose a system, choose a classifier, and evaluate their work with just that classifier. So there's no way to evaluate all these systems in an even ground. Unobservability assessment is only based on a limited set of features. As I said, just the frequency distributions of interpacket timings or packet sizes. And they also do not leverage recent advances on machine learning techniques. So our goal is to understand whether these protocol tunneling systems are secure. And to do that, we try to provide an answer to the following three questions. The first one is to understand how effective these detection techniques really are today. we want to assess whether other classification techniques can actually give us a better results in identifying these kind of systems. And we also would like to understand which features can be better be used to detect these covert channels, because there are a lot of features that can be used which are not directly related to the frequency distributions of packet sizes or timings. So we conduct the first experimental study on the unobservability of the covert channels produced by these multimedia protocol tunneling tools, and we make the following three main contributions. The first one is that we compared the existing similarity-based classifiers on the detection of multimedia protocol tunneling tools, and we see that in general they are not able to detect these covert channels accurately. Our second contribution is the exploration of multiple machine learning techniques for detection of these covert channels. And we found out that decision trees-based classifiers actually can detect these covert channels quite well. And lastly, we analyzed the importance of multiple features for the detection of these kind of systems, finding that packet lengths actually matter the most for detecting multimedia protocol tunneling. So in our work, we studied three multimedia protocol tunneling systems, which are kind of state-of-the-art. The first one is Facet, which actually permits a client within a censored region to watch a YouTube video. So how it works is the client sends an email, a steganography marked email, to a Facet server. The Facet server downloads the requested video from YouTube, embeds it into the actual call of Skype, and the video can be scaled on its dimension to accommodate for differences in traffic patterns. And then the client could watch its video. The second system is CovertCast, which works in YouTube live streams, and basically it scrapes the content of websites and transmits it through live web streams on YouTube. So it allows multiple clients to demodulate the content and access, for instance, news websites. The last system we analyzed is DeltaShaper, which kind of merges two of the ideas of both Facet and CovertCast, enabling for arbitrary data transmission of a TCP/IP stream. So basically, the IP packets are encoded into these colored matrices, are embedded into a call video, and it can also be scaled depending on the throughput that we want to give the channel and also the unobservability properties that we want to achieve. In this presentation, I will mostly focus on the analysis of Facet, but I invite you to read other interesting results that we have on our paper about the two remaining systems. For our adversary model, we actually emulate a passive state-level adversary, which is able to inspect the encrypted traffic streams of these multimedia applications. And we assume that the adversary cannot decrypt these encrypted traffic streams, neither to control any of these applications on the client side. We also assume that the adversary does not collude with the providers of these multimedia applications, and thus the only way that the adversary can actually understand and try to detect these covert channels is by inspecting encrypted traffic content, not being able to disclose the actual video feed that is being passed in the call. For our experimental setup, we have set up a local testbed into Ubuntu virtual machines, and we use Skype for Web for actually conducting Facet and DeltaShaper connections, and we use YouTube with the quick packets in Chrome, in Windows, just as the original system was proposed. For building our dataset, we conducted a gathering of traffic for 1,000 chat streams of Skype, and we built 1,000 covert streams by downloading some other videos from YouTube and passing them through the covert channel. For DeltaShaper, we did a similar thing. We actually transmitted 300 chat streams and built 300 covert streams. And for CovertCast, we crawled 200 live streams on YouTube and then built 200 covert streams for building our dataset. And we collect all this traffic for each sample for 60 seconds. So it should be a fairly small time interval for trying to detect whether a covert channel is active or not. So the first thing to try to answer our question on how effective existing detection techniques are today, we surveyed the classifiers that were proposed before, and here I'm going to be just referring to them as using the similarity metric that they use for building the classifiers. So Facet was using the chi-square test, CovertCast was built on a Kullback-Lieber divergence, and DeltaShaper was built on the Earth mover's distance. Albeit all these systems classifiers differ a little bit, their feature sets are similar. So all they used quantized frequency distributions for packet sizes or interpacket times, and in the case of Facet, actually the packet size diagrams were used. This table shows us the accuracy in detecting facet by using the 3 different classifiers. And here we can actually try to come up with 2 different conclusions. The first one is that the chi-square classifier was in fact the most accurate classifier for detecting facet traffic, achieving an accuracy of about 74%. And that later classifiers actually achieved worse results, only being able to have an accuracy of 57.5%. More than this, while accuracy is an interesting indicator of how detectable these covert channels are, adversaries are actually interested in evaluating the true positive rate and false positive rate trade-offs, because adversaries want to block the majority of these covert channels without blocking a high fraction of legitimate flows. For assessing these kind of trade-off, we built a ROC curve, which plots the false positive rate of the classifier versus its true positive rate. And here you can see that the perfect classifier, which will tag all covert channels while not tagging any legitimate connection as a covert channel, will be in the top left corner, so with a true positive rate of 1 and the false positive rate of 0. And here we can see that for Facet, if the sensor would like to block 90% of all Facet traffic, it will incur in 45% false positive rate when using the chi-square classifier, or a prohibitive 84% false positive rate when using the Earth mover distance classifier. So clearly, similarity-based classifiers are not suitable for the effective detection of Facet, and maybe we can do better. And that's what we try to assess next. We assess the effectiveness of multiple decision tree-based classifiers, in particular the extreme gradient boosting technique, which have been proved to offer good results in Kaggle machine learning competitions, and was also part of the solution from the KDD Cup. As a bonus, these models are very easily interpretable, and they also provide the ability to assess feature importance, which goes towards our goal of understanding which features are more important to detect different covert channels. We use 2 feature sets in our work. The first feature set is a set of features which were never previously considered for the detection of multimedia protocol tunneling. And it consists of a total of 166 summary statistic features, including also bursts in traffic. Our second feature set is we revisit the latest classifiers for multimedia protocol tunneling systems, and we also use the quantized packet lengths. However, we have a different insight for using these same features in the decision tree-based classifiers. Because while similarity-based classifiers just output a number for the dissimilarity between 2 frequency distributions, by feeding these same features to decision trees, we can actually try to check which range of these packet lengths are actually more interesting for performing the detection between regular flows and covert flows. First, I show you the results of extra gradient boosting while using the statistical features, so our first feature set. And you can see that for blocking 90% of all covert traffic, we just incur in a 7% false positive rate. This means that the majority of these covert channels can be flagged with a low false positive rate, and that it shows a large improvement over the previous classifiers like chi-square, which had a false positive rate of 45%. Interestingly, our results are even better when we use our second feature set of quantized packet lengths, and we can reduce our 7% false positive rate to just 2%. Then we try to assess which features are actually better to identify our covert traffic. And first, we try to analyze which features were the best in this set of 166 summary features. And actually, the ones that were more interesting, the top features, were actually related with packet sizes and burst timing information. And so it comes to no surprise that actually quantized packet lengths actually achieve a lower false positive rate. And we can see that when analyzing these kind of features, quantized packet lengths, actually the features that are most important in this traffic are the range of packet sizes, which are typically related to the ones that carry audio traffic. And thus the modulation that Facet performs on audio data is very easy to detect whether it is a covert channel or not, as the audio of a regular Skype call is probably very different if you are transmitting a video from a riot on a street, for instance. Even if extra gradient boosting was found to be very effective, it still requires a fully labeled dataset. And it is possible that adversaries in the wild may be unable to synthesize such traffic. And this may be because the sensor can actually have the difficulty in obtaining a particular multimedia protocol tunneling tool and synthesizing its traffic, or also because we can imagine the occurrence of zero-day multimedia protocol tunneling tools, which are not widespread, but still the sensor would like to block them. So we investigated the effectiveness of semi and unsupervised machine learning techniques, and we actually studied 3 different techniques: one-class support vector machines and autoencoders for building legitimate models of data. And we actually, these classifiers are very, can be tuned by hyperparameters. So we conducted a grid search over the space of parameters for these classifiers, and we will report the best results that we have achieved. Lastly, we used the isolation forest algorithm that can be trained without labeling any samples. Our results show that isolation forests are actually unable to accurately detect these covert channels by having just an area under the curve of this rock curve of 0.56%. And I recall that an AUC of 0.5 is equal to random guessing. Our one-class support vector machine performed a little bit better at 0.63 AUC, and our shallow atom encoder actually achieved 0.7 AUC. I stress that our autoencoder is a very shallow autoencoder structure with just one hidden layer, so probably more sophisticated autoencoder architectures may actually be able to detect accurately covert channels. And this is a problem for people trying to circumvent censorship. Lastly, I would like to give you an overview of our results when detecting the other multimedia protocol tunneling tools. I will start with DeltaShaper. So actually our results with DeltaShaper actually follow the trend that we've seen with Facet. For instance, for blocking 90% of all DeltaShaper traffic, we will achieve a 51% false positive rate while using the K-square classifier, while if you use extra gradient boosting tied with quantized packet lengths, we can drop that false positive rate to just 14%. Additionally, we actually detected CovertCast even using the similarity-based classifiers proposed before, which hints that the system is actually no longer secure, and that these multimedia protocol tunneling designs may be affected by implementation decisions taken forth on the protocols where they happen. And actually contacted the authors for CovertCast, and this was also one of these main concerns. So by concluding, I would like to conclude my talk by saying that existing multimedia protocol tunneling tools can be effectively detected by our decision tree-based classifiers. The analysis of feature importance can offer potentially actionable data for the deployment of new multimedia protocol tunneling designs. So for instance, for Facet, we've seen that audio modulation should be better performed. And we also checked that more sophisticated semi-supervised machine learning techniques can be promising for detecting multimedia protocol tunneling tools. Thank you for your attention. I'll be glad to answer some questions.
So also, please don't feel shy about coming up and asking a question if you have one. I know that sometimes. Oh, actually, here we go.
Thanks. So I noticed in your training set you had 50% positives, 50% negatives. In the real world, there's far fewer people circumventing than not circumventing. So I'm worried you're setting yourself up to commit the base rate fallacy.
So actually, we report in our paper another experiment where we shift the ratio of these kind of samples. So we actually tried with a difference of 100 to 1. Given the size of our data set, we wouldn't be able to stress that much further, but our results have shown that our results, the results I reported here in the presentation, are very similar. So I hope that answers your question.
So I'm also curious about sort of a way you would see forward in this area. Do you think that we should be trying to provide stronger theoretical guarantees if we're trying to do protocol tunneling or things like that? Or what would be your approach if you were trying to do this?
Yeah, sure. In our future work, we will try to establish these multimedia protocol tunneling approach in a more theoretical way. And one interesting way to do this would be, for instance, to just analyze the video feed that you want to transmit before you transmit it, and try to have some theoretical model that could say whether your transmission will get detected or not. So we would like to assess from an information theory perspective whether your current connection will trigger an alarm or not.
So you showed the most important features that you use to detect these protocols. I'm wondering if the applications themselves, knowing which features are the most important, change your behavior. Would that affect the way you can guess which ones they are? And then also, does this set up an arms race, or where do we go from here?
Yeah, I guess so. Today we are already on an arms race, trying to fight these censorship techniques. Actually, one further step will be try to decouple from the classifier, and I recall a talk from Pets in last year, which actually had a similar idea for fighting website fingerprinting, where the idea was to, given a given set of features, try to come up with a classifier which will be giving a lower bound on the possibility of detection. So this can be something that we can apply also in our work to check, but feature engineering will take a toll on performing detection. Yes.
So you didn't say too much about your feature space, particularly these higher order ones, but I wonder, are these the kinds of things you can actually detect on the fly, or is this going to be a case where the sensor can figure out you're circumventing only after you're done with your communications?
So we try to classify it while taking different timing samples from the covert channel. So for instance, if you are using a system like DeltaShaper to transmit, let's say, a text file, it will be probably taking longer than 30, 60 seconds. So answering your first question, no, the transmission probably won't be finished by that time, and the sensor can actually try to detect it much easier. The results I reported here actually show the results for traffic capture of 60 seconds, but you showed that even 30 seconds is enough, and we can even stress that further to, for instance, just 10 seconds.
Thank you.